Hey, welcome back. This video is just going to go over how to actually digitize some data so that you can generate relationships and parameterize your constraint analysis. And in class, we talked about the takeoff parameter method for determining your takeoff distance for a jet aircraft or any kind of aircraft. So I'll show you how to digitize a physically printed document using this software that I like to use called Engauge Digitizer. I'll put a link in the description below. But essentially, I've taken a picture from the NASA report written by Lofton. So in that report, they include takeoff parameter plots and plotted points for several different kinds of aircraft for different categories. So the one I'm looking at here, figure 3.7, is just looking at jet-powered aircraft, and it plots the takeoff parameter on a range of 0 to around 300, and the FAR field, or the FAR takeoff field length. FAR is Federal Aviation Regulations, and that length is in feet and ranges from 0 to around 13,000 feet. So the different symbols indicate the different type of aircraft, but they all tend to follow this nice trend line and the trend line that the authors put in. So if we want to, we can digitize the raw data. And using this software, it's nice and easy. All you have to do is select this option, and then you would select your 3 points along your axes that define your coordinates. And then you select your curve with this option here, and you just start selecting the data points. And it shows up as this smooth curved line just because of a setting I have it on. But once you've selected all of those points, you can export that as a text file or just a table, and then you can import that into Excel. So that's exactly what I did. And the result is, if we go back to our constraint table now, we have our takeoff parameter for each of those data points and the corresponding takeoff field length. So what I want to do to parameterize this is I want to find a line of best fit. The Lofton report used a linear best fit. I'm going to take a look and see if maybe there's a better best fit for that data that's shown, but linear best fit is probably the simplest. So what I'll do, I want to, if we think ahead, in our constraint analysis, we want to find our takeoff parameter as a function of our requirement, which is our field length. So if we change our requirement, it would be nice to automatically update our takeoff parameter instead of having to look back at a table for every single iteration. So if that's the case, I want a function of takeoff parameter as a function of the field length, whereas the figure that's shown is the inverse of that. So when I make a plot, I want to have my takeoff field length as my x-axis, and I want my takeoff parameter as my y-axis. So I'll have to go and do some manipulation afterwards, but it's pretty straightforward. So I'll insert this chart. Leave it as just points. So here's our graph. This looks very similar to the image we just copied. Now to change the x and y coordinates, the easiest way I can think of is just by moving these around. Ooh, I have to select the data first. I'll select the data, and now it'll allow me to move them individually. And I'm just going to swap the x and y. So it looks the same. It's a linear relationship, more or less. But now we have our takeoff parameter, our field length on the x-axis and our takeoff parameter on the y-axis. So the next thing I'm going to do is I'm going to add a trend line. So we have a linear trend line that seems to fit pretty well. We could choose a power trend line. To see which one is fitting the data better, we can plot our r-squared value. So you can see I'll make this a bit bigger. Let's make everything bigger. So we can see our r-squared value now for the power log fit is 0.9593. If we choose a linear, we get basically the same fit. So a linear relationship is easier to deal with. So let's just leave with the linear one. We can display the equation on the chart. And then so we have a function now to parameterize these values. And we can hard code in what the takeoff parameter would be as a function of our field length. So I'm going to take this equation, 0.0291, and I'm just going to copy out these parameters over here. So if we have our equation of a line, all right, takeoff parameter is equal to S landing times 0.0291 plus, or in this case, minus 20.124. So I'll just keep this in mind for me. And then when I go over to the right-hand side over here, where we have our takeoff parameter in our equation, what I'm going to do is I'm going to take our landing distance, so this is equal to our total landing distance, that's our far total landing distance, times 0.291, I'll double check, minus 20.0291 minus 20.124. Right, so we had a takeoff parameter of 96 roughly if our total landing distance, or sorry, total takeoff distance is 4,000 feet. So that's a quick way that you can just digitize data, and it's as accurate as the data plot itself. In Engauge Digitizer, you can zoom in, zoom out, so you can get as accurate as you want to. But again, we're just finding a trend here, so we can parameterize this. The data is a bit scattered, so it's just an approximation for one of the methods for estimating your takeoff field length and your thrust weight and wing loading constraint based on that requirement. So in the next video, we'll actually look at starting to plot our wing loadings and our thrust weight ratios for stall and our climb requirement.